Okay, so that was generalized least squares as a general procedure to deal with non-spherical errors. The practical difficulty, of course, that we've seen is that we may not know omega, and our estimate of omega in feasible generalized least squares could be easily misspecified. So in this final substantive part of the lecture, I want to very briefly outline an alternative approach, just 2 slides, that's widely used in practice, and it's called robust inference. The setting is the same. The error covariance matrix is not sigma squared I times the identity matrix. The OLS estimator remains unbiased under exogeneity, but the usual covariance estimator, S squared times X transpose X inverse, is no longer valid. Robust inference takes a different philosophy from GLS. Rather than modelling the error structure itself and trying to represent it, we keep the OLS coefficient estimates and simply replace the covariance estimator with one that remains consistent under non-spherical errors. That's what we're going to do, focus on the covariance matrix. Now the robust estimator has the sandwich form shown on the slide. Sandwich form here, this is in the middle of the sandwich. So we have X transpose X inverse times S hat times X transpose X inverse, where S hat is going to be chosen to account for the non-spherical error structure, and it's computed from observables, essentially the residuals in the data. But we're going to choose it in a way that it's going to remain consistent under non-spherical errors. So crucially, 3 features of robust inference are as follows. The coefficient estimates are unchanged. We're not touching the betas. The standard errors, confidence intervals, and hypothesis tests are going to be corrected, but there's not going to be an explicit model for omega. That's not required, which is exactly what makes this approach so attractive when we know very little about the true error structure, or we simply aren't interested in it. And the table here briefly summarises 2 robust covariance estimators that you'll encounter in practice, and I'm not going to go through the technical detail of them. I'm just going to explain at a high level what the idea is. So for heteroscedasticity, the robust estimator is called a White estimator. The idea is that we use the squared residuals, EI squared, to estimate unknown error variances, replacing each unobserved sigma squared I with the corresponding squared residual. That gives us a consistent estimator of the problematic middle part of the sandwich. And note that if the squared residuals happen to be roughly constant across observations, the White estimator is just going to reproduce the standard OLS standard errors. For heteroscedasticity and autocorrelation together, the Newey-West estimator, also called the HAC estimator, for heteroscedasticity and autocorrelation consistent. This uses both the squared residuals and the lagged residual products, ET times ET minus 1, to estimate the covariance matrix, allowing for correlation between errors that diminishes as their separation in time increases. So the rule of thumb for the robust estimators is as follows. For robust inference, use White standard errors when heteroscedasticity is suspected, use Newey-West standard errors when observations are ordered in time, and autocorrelation may also be present.